I think the very simple answer is everything that is around you is made up of stuff, and that stuff is made up of chemicals or elements, atoms with electrons. So ever since I can remember, as a kid, when I was playing in the dirt or looking at plants or thinking about electronics, I realized the substrate of everything was chemistry. And also, I guess through several accidents of schooling, which are probably too long and boring to go into, I always wanted to be a cross between a physicist, a mathematician, and a computer scientist. But I wasn't able to communicate my enthusiasm. Well, I was able to communicate my enthusiasm, but my educators saw no potential. And so in the end, I clawed my way to chemistry, which was really very fortunate because I find chemistry extremely productively confusing. And so I think in a way, physicists are kind of lazy chemists. Computer scientists are even lazier physicists, and mathematicians don't want to bother with reality at all. And that's kind of a joke, but I think it's kind of like, I think I can build my entire reality from chemistry up, and one day I might end up in abstract mathematics with those great minds. It's a really important question, and I prefer to kind of sidestep all the endless definitions and criteria because, if you say, oh, I'm alive because I do this, if you freeze me for 1 attosecond, that's 1 times 10 to the minus 18 seconds, and photograph me, I will look no different to that of a rock. Nothing will be moving. And so, okay, if you freeze a rock at 1 attosecond, you'll get the same thing. And so I realized that there is no difference between inanimate matter and matter, except the fact that animated matter is a long lineage of machinery or selected objects that can exist for longer than their natural half-life. So what I mean is if an object could break apart in the wind or in the rain or dissolve, let's say in 1 second normally. So if you had 100 of these objects, and in 1 second, 50 of them would be gone, and the next 1 second, 25 of them would be gone, and the next 1 second, 12 and a half of them again, like an exponential decay. That object is just naturally decaying. So when those objects are able to persist for many times longer than their natural half-life, some process must be going on, some kind of copying, harnessing of the environment. And that lineage constitutes some kind of propagation of contingent information that is through selection. And so selection creates machinery or systems that defy decay, natural decay. Now, that's actually quite a new definition I've only worked out in the last few weeks, just to make it really narrow and really precise. But the other thing is that I like the most is that living systems create complex objects at scale. And when you see evidence of a living system in the complex object, that's to do with that lineage. But those lineages are characterized by objects that have this lifetime. 100%. I think it's kind of interesting for me that I started the base layer at chemistry, because the base layer to get to selection is making chemical bonds. And then you get to cells, but it doesn't stop at chemicals for cells. You have tissues, and then you have organisms that move, and then those organisms start to be able to sense the environment. And with sensing, they build symbolic representations and abstractions. With those abstractions, those symbolic representations, they build kind of language and culture. And then with that, they build technology, and that technology then enables their culture to be supercharged in some way. And it carries on and on and on and on up these layers. But the base layer seems to be the chemical bond, which is kind of fascinating. The chemical bonds are responsible for memes. But I would absolutely agree with you. But what we mustn't do is mix up the layers of abstraction. Like assembly theory applies to bonds, in molecules right now. You could then go to assembly theory in tissues, and then in organisms, and then in abstraction, and then in technology and in culture. But they are separated, they are layered. And I'm still working out what that means. For me, I am way out of my confidence on this, but I think there are a lot of very smart people working in these areas who can see similarities. But yeah, I think you're right that it's just it's a natural progression. Okay, very interesting. I think the cellular automata are very nice representations of mathematical entities. So the fact we can use mathematics to represent evolution is kind of what Stephen is doing with his systems, and that's nice in a way, because you get to play with a new kind of system. Um, I think that in that regard, molecules are not mathematical descriptors of themselves. So one way of arguing would be to say, could we use CAs to mimic molecules undergoing evolution? Sure, we can. Stephen has shown that quite beautifully. But is that the most computationally efficient way of doing it? And I think that the answer is no. And what Stephen is doing with CAs and his Ruliad is introducing a beautiful but complicated and cumbersome, ultimately cumbersome architecture that doesn't really give us any more knowledge or any more predictions or any more conceptual understanding. However, that doesn't mean it won't yet, right? And so I'm excited for Stephen to try it, and I would be the first to use it if I can find out how. Now, thinking about molecules and CAs, well, molecules are a bit different. The rules of the molecules don't come from some kind of abstract lookup table. They come from their interactions with each other as controlled by the laws of physics, as controlled by the periodic table and quantum mechanics. And so I've been trying to, because I love CAs, to find out a molecular version. I've actually made a chemical CA, but it required so much infrastructure. It required digital electronics, stirrer bars, a thing called the Blues-Sabaskinsky reaction, which is an oscillating chemical reaction, which oscillates between blue and red, depending on the dye, analogous to the black square and the white square in the CA. I had to 3D print grids. So I'd had to do an awful lot to make chemistry interact in CAs. So I don't think there is that much relationship. That doesn't mean people shouldn't try and use them for new things. But I'm a kind of a first principles type of guy. When I go to first principles, if the layers of control can be replaced by a simpler one, which has all the functionality, I just go with a simple one because my mind is not big enough. That you're asking the small questions today. So let's go back to self-replicating molecules are kind of important in chemistry. They do something at the interface in our reality, which we'll come back to. When it comes back to the computer, I think that it is computational universality did not exist at the beginning of the universe, I think. David Deutsch and Stephen Wolfram will disagree with this quite fundamentally. Computational universality was produced by evolution about a few hundred years ago, or probably with Descartes, and then going through with von Neumann and Alan Turing and Alonzo Church and our ability to have languages. So we have only really come up with universality just recently. And I think Deutsch would agree that we've only started to use it. Now, does that mean there is some computer elsewhere in the universe that's been made by aliens and selection? Sure. But you have to ask yourself, if you go all the way back to the Big Bang and start the universe, that's the accepted beginning, and propagate forward, Big Bang has to give rise to stars, galaxies, right? Explosions, planets, evolution, and technology. I don't see how asking the question about the computers exist in the universe makes any sense. And I think this is kind of a bit about the ontology versus the epistemology, right, of a situation. Like, is something a model? If something is a great model for something, does it mean it is that? And I think we kind of get stuck and we lose something until we are able to accurately predict the future with no errors with some technology. Then we know the universe is computational, but it's not. In fact, the universe is not computational. In fact, Stephen Wolfram himself admits that when he talks about computational irreducibility. Parts of the universe are computational. And so I think that actually life in some regard is non-computable. And I don't know why that is. It doesn't make any sense to me looking back in the past. Look forwards into the future and applying selection, it does make a great deal of sense. But I'm unable to express that in ways that someone who I respect very deeply, David Deutsch, would necessarily accept, although I haven't talked to him about that particular thing. I have talked to him about some aspects of it, but we haven't really got into that focus. It's a really hard one. And there's a belief system, right? Like Stephen Wolfram believes the universe is a computer. He can't prove it. He thinks he can, but that's but at the end of the day, there's a belief system there. And I guess I believe the universe isn't a computer, or more accurately, I haven't seen any evidence that would allow me to conclude that the universe is a computer at the base. That doesn't mean that computers cannot emerge in the universe. Now let's go on to your next point about aliens. Well, there almost certainly is selection elsewhere in the universe. Now, is selection a universal phenomenon to produce intelligence beyond Earth? We just don't know. It seems like it. And in those situations where selection produces life and then intelligence, would those creatures, if they were to see each other, be able to work out? I guess so, with certain provisos. You probably want to hook up with intelligence if there's like an intelligence Tinder in the universe. I don't know if it's like a kind of intelligence dating app. You probably want to find intelligence that emerged on rocky planets using chemistry, because the timescales for everything will be roughly similar and the locomotion will be roughly similar. So you'll be able to see each other move on similar timescales. And then if you've both sufficiently understood that life produces complexity and you can see weird artifacts produced by these intelligent populations that you can't explain using your laws of physics and natural phenomena, then you might start poking them and trying to then produce a kind of Rosetta Stone to work out how to communicate. So that's a very long way of saying, if you're lucky enough to hook up with the alien civilization via whatever version of, exoplanet searching, I would be optimistic that in time you would be able to recognize and communicate with them. I don't know. I keep reprogramming my memory to kind of think about what actually happened. Assembly theory is the theory that we've developed that can kind of help quantify selection in a very general sense. And assembly theory came about my struggles to try and understand how we can make the leap from sand to cells, without kind of having something fantastically improbable, which is not satisfactory, fantastically magical, which isn't satisfactory, and just by saying, oh, it is, right? So I wanted to understand, what is it about our physical reality where selection can act before biology? And assembly theory is kind of the answer to that. So assembly theory allows us to quantify when selection is occurring, has occurred, and most recently we're able to now predict when selection will occur, which is really exciting, which is just starting. So that's kind of cool. Now, how do we do that? Well, assembly theory has a number of major components. The first thing is assembly theory allows you to say, look for complexity more objectively than any other complexity measure has ever been generated before, because it is not requiring us to think about programming methods and data compression. Assembly theory is about finding objects that are composed of parts that can be reused and made, and then counting up the number of copies of those parts. So one example could be, imagine you found, I don't know, 100 iPhones, right? You might go, one for iPhone, or one object looks like an iPhone on Mars, maybe random. But if you found 100 iPhones and you could take them all apart and find the batteries and the cameras and all the other bits and bobs, you'd like say, no, there's something really odd happened here. They can't have all formed by chance. So that's kind of the genesis of assembly theory and what it does. And it really has those two components, the copy number, the number of individual objects, and then also how you can break those objects apart into reducible components to the irreducible building blocks and then create them on the shortest path. And the shortest path gives you kind of a lower bound on the amount of causal information or selection required. How did I come about assembly theory? Over many years, with many discussions with many people. But I think it really was me kind of working with a colleague at Arizona State University over time, Sarah Walker, where we were both saying, where Sarah had this conception of information in physics becoming life, and I was trying to understand how to tell if a molecule was produced by biology or not without having any information other than the molecule. And so when I realized that, and I imagined the molecule in my head, I was like, how complex a molecule must I have for you to go, okay, it's definitely been made by a human, an architect, or biology? And then initially all the chemists, and they still don't agree with it, right? I mean, assembly theory is causing arguments in some aspects of, well, actually, on the fringes, no one really disagrees, actually. There are some, the problem is there's some crazy arguments, and they're just so irrelevant. It's kind of, I shouldn't give them any airtime. But let me finish my thought. So complex molecule, and when I imagined it, people were like, but you could imagine a one-off complex molecule. But what I wasn't correctly articulating is when I imagined that molecule, I imagined detecting it with an instrument. And in chemistry, you don't just detect one molecule, you have to have a large number of identical molecules. And so it took me a few years. So Sarah Walker and I kind of came up with a basic idea. And then we were thinking about the reducibility and then realizing the copy number, which was the next idea. And now we're understanding how we then can explore the combinatorial spaces to then map out selection as it's going. And that's kind of assembly theory and its history. And in fact, it was an interface between me going to Origin of Life meetings and all the Origin of Life people saying it's impossible, and me going to artificial life meetings where all the artificial life people go, let's just make it, it's really cool. And there are robots and cool CAs and all this stuff everywhere. And it was kind of the juxtaposition of those two kind of dogmatic, well, one really dogmatic community and one really hippie, let's be a playful community. And I wanted to combine them together. So I kind of leaped from the Origin of Life chemistry community into the A-Life community, and that was the best fun ever. So, I mean, Kolmogorov complexity is really, it requires a universal Turing machine, which people say is trivial, but it's not trivial, right? It's a kind of, you have to have a machine. And then what Kolmogorov complexity does is says, look, what is the shortest program that does this thing, right? Whereas assembly theory basically says, what is the minimum number of steps I need to do to produce this object from interactions in the environment? And so the really simple answer is that Kolmogorov complexity and assembly theory are not related, right? They are really interesting. Kolmogorov was built for looking at complex mathematical problems using Turing machines, and it's fantastic for that. And assembly theory was built to find out when you have selection operating or not. What seems to have happened in the last 50 years is that people in computer science have increasingly used measures like Kolmogorov complexity, logical depth, and Chaitin-Kolmogorov complexity, which is the same type of thing. It's the same thing, algorithmic complexity, and assigned it to natural phenomena. And it just makes no sense. There is absolutely, unless the natural phenomena can be constructed by a universal Turing machine, then sure, you can then compare that and it's kind of fine. But then you get trapped into all these circular arguments and you get numbers out. It's a bit like Shannon entropy, right? Where Shannon entropy and thermodynamic entropy have some overlap, but they're not really related. And it's kind of, this is where complexity theory has gone along for the last 50 years. Like complexity theory, as far as I can see, doesn't actually do anything outside of computer science, and it shouldn't be. It was never meant to be that, right? And I think that's why it's taken such a long time for something like assembly theory to come along, because assembly theory basically allows you, if you've got a bunch of stuff, you can apply it and get an answer. With complexity theory, all the answers are contradictory, they're not consistent, you have to be labeling, you have to know the answer to get before you apply and get the answer. That's not very useful. Where assembly theory, you don't need to know the answer. You have two samples of material. I guess, if I'm being honest, I have no idea. I'm not qualified. The whole consciousness debate drives me to bemusement. There are three reasons for this. Number one, we have all the tech bros who think they're going to invent AGI, and without defining it. We have all the philosophers who are trying to either say it's special, say it's irrelevant, and then we have this idea that we'll just create consciousness everywhere, and that it will just be, kind of, it will be different. I think they're all wrong. I think it's not as simple as that. But I don't know, right? And so I'm going to get an honest answer. I think the easiest way to make a consciousness is to evolve one. And so basically start off with the origin of life, go all the way through and I think actually consciousness evolves in populations of intelligent human beings, or sorry, no, not human beings, entities with a kind of physical interaction. Is almost like some primitive culture comes before consciousness, which is weird. It's not, or they come at the same time, right? You're bumping into one another. So the fact you're bumping into one another, you don't want to hurt each other. You might want to find a mate, you want to find food. And so this kind of balance is that this communication with one another and your situational awareness gets solved by evolution, by generating this phenomenon of consciousness that is then shared and then somehow has been put into us. Now, does that mean we can't create machines that can do that type of thing? No, that doesn't mean that, but we just don't know how to do that yet. We don't know whether we're this close or this far. And I think the current fetishization with AI is actually incredibly dangerous, not because I'm a doomer, just because it's taken people's, it's basically inventing a religion. You have the religion of the AI and the AGI. You have the religion of consciousness is special, or you could just have the we don't know what it is yet. And so what I would like to do perhaps is to extend some notions from selection. Can we use some ideas from selection from assembly theory to extend into consciousness and culture? I don't know. And so I think it's quite funny to watch. But do I predict whether the consciousness will be made in a machine or not? My feeling is until we understand what the universe is doing, or let me put it another way, how the universe is able to mine novelty from the future and actualize it in the present, we won't actually know how to make a consciousness. So once we're able to do, I should do that, so I think once we understand, right now, our attempts to understand life and consciousness will probably show us how our current, and this is really wrong probably, but let's have a go. Probably our current view of the universe, our physics of the universe is incorrect. And that life is able to literally mine novelty from the future. And the most efficient way to do that is, other than evolution, evolution is quite good, but slow, intelligence and self-awareness is getting good. And then with technology and consciousness and interactions, higher level, we're getting even better at it, and we're generating all this stuff. So there's something about the way the universe is expanding in time, right? In time, that allows consciousness to exist on this wave between consciousness exists between the past and the future in the present, which is thick. And I'm a chemist, right? You know, it's kind of funny because I get into arguments with people who get very passionate, and I'm not qualified. I want to come up with an experiment though, so maybe that's helpful.